We're at a pivotal moment in the evolution of computing. Quantum computing is emerging, and experts expect the market to grow rapidly and continue to expand as the technology matures. This exciting opportunity has many people wondering how quantum computers actually work. It's not that quantum computers do the same things better than conventional computers. They do things entirely differently, which allows them to accelerate solutions to a class of impossibly complicated problems. Let's start by looking at how traditional computers work, like the devices that we use every day. Bits, short for binary digits, are the basic unit of information in digital computing. Each bit is usually formed from several microscopic transistors that can block or allow electricity to flow through them, representing 0 and 1. When grouped together, bits can store large numbers, and along with tiny electronic devices called logic gates, they perform calculations at breathtaking speeds. Quantum computers, on the other hand, use quantum bits, or qubits for short, and they store much more information than ones and zeros. While traditional bits are manufactured, most quality qubits take advantage of natural quantum systems. They are made of subatomic particles like electrons and hold infinite possible two-dimensional values. In fact, in quantum computing, these values represent probabilities, and a quantum algorithm can help identify multiple likely outcomes. Let's go over the fundamental physics concepts that make quantum computing possible. First, we have a concept called superposition. The idea is that a quantum system can exist in more than one state at a time, as long as you leave it alone. Imagine a sphere with an arrow spinning inside it. Mathematicians call this a vector. This vector can point down, representing 1, up, representing 0, or be in any position and angle between 0 and 1. In fact, every angle can be seen as a mixture of both 0 and 1. It's not binary. Superposition allows quantum computers to think not only in absolute terms of yes or no, but also yes and no. They represent the likelihood of scenarios or probabilities.
If you think about it too hard, your brain can hurt. But the theory works, and of course that same weirdness of quantum physics is what makes quantum computers do amazing things.
The second crucial concept in quantum computing is entanglement, a phenomenon in which the quantum states of two or more objects are correlated, even when the objects aren't near each other. It's as if you toss multiple entangled coins and they land on the same side every single time. This doesn't work with large objects in nature, but it is simply how things work at the subatomic level. Quantum computers use multiple qubits that operate in parallel. Multiple qubits can be grouped or entangled into little subsystems depending on the programming needs. When qubits are entangled, their values become intertwined or correlated without having any information flow between them. Entanglement and superposition allow quantum computers to deal more efficiently with highly complex problems that involve multiple probabilities. This is precisely where traditional computers struggle the most. Now let's merge these two concepts of superposition and entanglement and see how they help with calculations. A single qubit can hold a superposition value of both 1 and 0. In other words, one qubit holds two possibilities at once. When we entangle two qubits, together they can hold 4 combinations of superposition values. 3 entangled qubits, 8 permutations. 10 entangled qubits generate 1,024 permutations, and so on. If we entangle a 20-qubit system, it captures over 1 million combinations.
It's like compound interest, only the interest rate is 100%. You get to double every time you add a qubit. So when you get to a few hundred qubits, the number of possibilities is 2 to the power 100, which is enormous. This is more than the amount of memory on all the hard drives in the world. Okay, so a quantum computer with just 100 atoms, 100 qubits, would be able to sample data spaces that are much larger than we could ever possibly do with a classical computer.
As a result, quantum computers are uniquely suited for problems that grow exponentially in complexity. Traditional digital computers have a hard time with these types of problems as they have to be able to evaluate all possible options one at a time. And despite their seemingly incredible speed, the number of options in these types of problems simply outpaces any practical use. Quantum computers, on the other hand, use entangled qubits and superpositions to find the answer. They describe the range of possibilities in a problem and, through a series of manipulations, allow the entangled system to find the most probable solution, considering all options as impossibly numerous as they may be, all at once. Why does this work so well? Probability and manipulation. While traditional digital computers deal with deterministic or known precise values, quantum computers, and nature as a whole, always deal with probabilities. This means that some quantum algorithms don't find one exact value as the answer. Instead, they find multiple potential answers. In this case, the quantum computer will calculate the likelihood for each outcome and offer its probability. Let's say a chemist is researching new materials to improve battery performance. A quantum algorithm might conclude that there are multiple ways to organize a molecule, each with their own likelihood of storing energy. Then, equipped with this information, the chemist can choose the best material for the battery. That said, other quantum algorithms can process incredibly complex problems, evaluate many possibilities simultaneously, and provide a single correct answer. These two outcomes are not in conflict. It's just two different ways of using the power of quantum computing, sometimes looking for probabilities, and other times looking for a decisive answer.
The types of problems quantum computers excel at are those that actually are very poorly performing with regular computers. These are typically problems that have countless configurations, countless possibilities.
In addition to probability, manipulation is also key. How do we manipulate an entangled system of qubits? Using waves. We've all seen how waves in nature can either build upon each other or cancel each other based on their exact structure. Take sound waves, for example. Noise-canceling headphones listen to the noise outside of the headset and quickly cancel that wave before it enters the ear. On the other hand, speakers in a concert hall amplify each other's waves so the performance can be heard from a distance. We call this process wave interference. A quantum algorithm amplifies the right answers and suppresses the wrong ones until the best possible wave, the solution, remains. Now imagine that we're trying to optimize the path and energy consumption across rugged terrain. We can represent that terrain as a grid of entangled qubits. Once we describe the entire terrain, the system of entangled qubits represents all possible paths. Now we can define the rule for what's good, short distance and low energy consumption. The definition gets propagated multiple times, amplifying successful paths and suppressing long or costly paths. In the end, we are left with only the best path that requires the shortest distance and least energy consumption. This is a very different approach than a traditional computer, which evaluates each potential path one by one. Although each individual route is quickly assessed, there are so many potential paths that it would take a conventional computer far too long to find the optimal way. So to sum it up, quantum computing is the practical use of subatomic particles for calculation. It leverages superposition and entanglement to manipulate qubits. The qubits contain all possible answers to a very complex question. Then, using wave interference, all the wrong answers get canceled while only the best possible solutions remain. In the next video, we will explain IonQ's unique approach to quantum computing and its clear advantages in practical use.